All right, and we're back. So we're looking at sort of this equality here. One of the ways to think about how strong Earth's gravity field is that it exerts 9.8 newtons of force for every 1 kilogram of mass. Okay, so I think yesterday we looked at this kilo over here. So here is 1 kilogram of mass, and as it rests on my hand here, so you can see it, Earth is pushing down on it with 9.8 newtons of force on my hand, which is my hand has to put 9.8 newtons of force up, in order to support it here. Otherwise, it would accelerate in the direction that the net force is going. So when something's stationary, it's because the ups equal the downs, right? The lefts equal the rights. The forces are balanced. I myself, you may recall from yesterday's calculations, have a mass of 100 kilograms. And so for every kilogram of mass that I sort of possess here on the surface of the Earth is exerting 9.8 newtons of force on it. So it's force per unit mass. Well, I have 100 units of mass, right? I'm 100 kilograms, which means my weight, the force due to gravity is my weight, is 980 newtons, right, in the SI units. But about 220 pounds, okay, in our sort of US customary units. So 220 divided by 2.2 pounds per kilo, there's my 100 kilograms, and then 100 kilograms times 9.8 gives me my 980 newtons of weight. Everybody can clearly see that. No worries at all. Everybody on YouTube's like, what's he pointing at up there? That's like the key to the whole lesson. We're missing out. The Drake equation will have to, wait a couple of weeks on that. That's really good stuff too. I'm talking about this guy up here. F equals ma in general, but when the force is the force due to gravity, you got weight, mass times the acceleration due to gravity. So your weight is the force due to gravity. Force due to gravity equals mg, or weight equals mg, where g is 9.8. But we also said it's an acceleration vector. It's the acceleration due to gravity, which says things get 9.8 meters per second of speed every 1 second they fall on Earth. That's another way to think about what Earth's gravity field strength is. It's an accelerator that speeds things up. This is about 23 miles per hour. So every second you let something fall on Earth, it picks up 23 miles per hour of speed. So if something falls for 2 seconds, it's going 46, and so on. So that also is a way to sort of measure a strength of a gravity field. Does it accelerate things a lot? Is it a lot of force per mass? And then is a Newton per kilogram the same thing as a meter per second squared? So if we pulled up Newton's second law of motion again, we can say this relates force, mass, and acceleration, but we measure these things in units. So force measured in newtons, mass measured in kilograms, acceleration measured in meters per second squared. This tells us how we define the Newton. 1 Newton of force is the force required to accelerate a 1 kilogram mass 1 meter per second squared. 1 meter per second squared times 1 kilogram is 1 Newton. A Newton is a kilogram meter per second squared. A Newton is a kilogram meter per second squared. That's what a Newton is. So a Newton per kilogram is surely meters per second squared. Okay, it's the same exact units. Different ways to think about it. Force per mass, acceleration. Okay, Earth's gravity field. So here's what we want to do with this now. So that's again your quiz before the end of the class period, or sometime over the weekend, or maybe Monday. You send me pictures of all your journal pages. You can leave it here on the lab benches if you're in person, and I'll grade it, probably sometime on Monday before 4th period. Hopefully, it won't be like 4th period starts. I'm like, oh, let's go. These journals are great. And then you'll have it back then. E-learners, remember, just scan copies of all the pages of your journal. And email it to me. So I want to sort of develop a procedure here for when we go out into the practice field. We're going to launch rockets. Okay, so it's the point of it, let's study some gravity fields here so that we can go out and launch rockets and see how that massive object, a rocket, moves. Massive objects move in Earth's gravity field. Today in the lab, you can kind of see I've got a little projectile motion apparatus set up here, so we can just kind of explore it a little bit inside of the lab. But then the idea would be to go out, and we'll be the projectile launchers, not the marble launcher, but we'll, throw tennis balls and launch rockets and things like that. So let me give you a procedure here for when we go out there, how will you go about sort of doing that? That won't be tough for you guys. You can see the whiteboard, so I think what I'm going to do now is all right. So we want you all to be able to calculate like how fast, how high. And I throw a physics sphere, tennis ball, or marble, whatever. All right, so that's actually not one. That's the question. Those are the questions we want to be able to answer. And the only data that we're going to collect, now that we've established that Earth has an acceleration vector of 9.8 meters per second squared, the procedure is going to be to like time a throw. Let's make that a little bit more clear. Let's say throw a sphere in the air and measure tough to read, huh, you guys? Throw a ball. Measure time airborne. All right, so that's pretty much all we need. If you throw a ball in the air and you time how long it's airborne, that's enough. Now that we know gravity, calculate how fast you threw it and how high it went. And if you want to, we could just say, well, let's try to just throw the ball directly vertically. That's kind of tough to do mechanically, like throw a ball like this or do like an underhand throw or something. But if we throw it down range, then some of our energy is like not going against gravity. It's just going to sort of go to sort of lateral motion, which is fine. So it really doesn't matter. But we want, I mean, if you throw a ball sort of down range, you can still calculate like how high up it went because the time airborne is that's all that sort of matters there. It doesn't matter how far down range it lands, gravity sort of acts on it the same. So timing something, you'll still be able to sort of determine this, but the how fast you throw it will only be able to determine the vertical component of your motions. Like if you throw a ball, say like at an angle this way, right? So there's an angle here. There's a component of my throw that's going up and a component that's going over. The data that we're collecting here, the time data, like gravity is the only thing that affects that. And so we'd only be solving for how fast, like this way we threw it. So if you throw it entirely this way, then you get the total speed. By measuring the range of the projectile, like if you throw it down range and then you go and like count how many paces the ball lands away, or measure it more precisely than that, then that is enough to calculate the entire vector. We could say like how fast did I throw a ball. But I like this procedure for, it's very straightforward and simple. You can measure, say, babysitting. It's like, okay, hey, we're gonna go outside, you're gonna throw a ball in the air, I'm gonna time it, and I know enough physics to tell you how fast you threw it and how high up it went. Like we're gonna be able to reach those conclusions. So let's just adopt the procedure of when we go out, into the field here for the first time. We're gonna try to just throw a ball straight up in the air, we'll let it go up, we'll let it fall down, and we wanna know how high up did it go and how fast did we throw it, okay? so how fast, how high, those two things. To calculate how high up it goes, we use the equation 1/2 gt squared. All right, so without taking the time to derive this equation of motion, you just take it as true for me that the height of something in a gravity field is related to the time it takes to fall by this equation, where this g is what we call local g, right? So this is Earth's local gravity field strength. It's local here to Earth. It's not like the universal gravitational constant, big G. So we'll just replace that acceleration due to gravity with just a lowercase g. So if you time how long something is airborne, we'll call it capital T, this time would actually be half of that. This is the time it would take the ball to fall from maximum height, okay? So if it goes up in a certain amount of time t, lowercase t, it's going to fall in a time capital T, it falls in the same time lowercase t, so the total time capital T is twice lowercase t. So if you measure the total time airborne t, then the next thing you're going to do is, let's call this step 2, t divided by 2 equals t, lowercase t. All right. And then with that, you could go to step 3 down here, calculate the height, right? So it's just whatever that number is, t, that's how much time it took to get to max height, square it, times 9.8, times 0.5, that's how high up it went in meters. Okay, let's remind ourselves that there are 3.28 feet equals 1 meter. So that way, when you get this answer, you can just multiply it by 3.28 and go, oh, that's how many feet. The how fast, we'll calculate like, yeah, that's it.
I was going to say, are we going to use the velocity equation like an equation of motion?
Yeah, and that's what this is too. This is one of the equations of motion. It's just a piece of it. So we throw a ball up in the air with velocity, some velocity v, but at the top of its flight here, it reaches, sort of like a temporary final velocity of 0 meters per second, right? Gravity slows it down to a stop. So the initial velocity, vi, the final velocity, 0, and we're going to measure how much time it takes to get up there. So we want to solve this. This will be our unknown. We're going to know velocity, acceleration, and time, and so the equation, we'll call this step 4. It's actually the first question, how fast, is going to be v equals, well, I can really hear the gears turning in my brain. I'm thinking hard today. Everybody else, there's that too. The final velocity is 0. The initial velocity is the thing we want to know. Gravity is going to slow that down, 9.8 meters per second squared times the time. So really, if you think about this, like you're going to throw the ball up. Oh yeah. You're going to throw the ball up with some initial velocity. And then gravity is going to act on it for a certain amount of time until it's 0. Okay, so it's like saying, once you know how much time it took gravity to slow it down to a stop, multiply that by 9.8, and that must have been the speed that you threw it up with. In other words, this term here, 9.8 t, will be the negative of the positive velocity that you threw up, because whatever speed you threw the ball up with, this term here is, whatever value it is, it's the negative of it. That's how it's 0, right? Like, let's see that number. Let's say it's 1 second. You throw a ball, and in exactly 2 seconds it hits the ground, which means in 1 second it was at maximum height. So we'd say, I must have thrown the ball 9.8 meters per second then. Because 9.8 meters per second minus 9.8 times 1 second is 0, right? So that's how we get 0. I think it's very worthwhile to not just say, here's an equation, 0 equals this number minus 9.8 t. I think it's helpful to say, this equation tells me how much time does gravity, which is this strong, 9.8 meters per second squared of deceleration, how much time does gravity need to act on this velocity until it's zero. It's really what we're solving for. And then we'll know what our initial speed was. So computationally, we can just say vi so vi is going to be what? Just 9.8 t. It's going to be multiply 9.8 times t. And the reason why that works is because, you know, that's the negative of our positive velocity, because we know at the top of its flight, gravity slowed it down to zero. I don't think anybody's going to throw the ball with such velocity that it like goes in orbit. All right, it's going to come to a stop for a moment and then come right back on down. And so that's how you can determine your initial velocity. Keep in mind that because 9.8 is meters per second squared, like we showed over here, your velocity will also be in meters per second, which you can then multiply by my birthday, February 23rd, 2.23, and then it becomes miles per hour. So we're going to do the calculations, the measurements in such a way that we're going to know how many meters high the ball went. But we're probably going to be interested to convert that to feet. So you can say, like, oh, I can throw a ball this many feet in the air. We're going to know our velocity. We can throw a ball this many meters per second up. Or we're probably curious to know how many miles per hour that is. So we want to be able to like do those conversions as we get our final conclusions. So just kind of keep that procedure, you know, somewhere handy in your journal that you can reference it. You might want to take some time today to kind of clean that up a bit. That's kind of just all over the board there. But you might say, oh, let me go to a clean page here and kind of straighten this out. Throw a ball and measure the time. Take the time, divide it by 2, so you know the time to max height, and then plug it in here, which is 9.8. Right, we derived it theoretically. That'll tell you the height in meters, which you can then multiply by 3.28. You know, how many feet tall the ball. And then it doesn't matter what order you do these calculations in. Like I said, how fast, then how high. So you can do how fast first, right? You could. We're measuring t, right? So we're using stopwatches. You're going outside like a ball and a stopwatch. That's all you need, and a knowledge of physics, right? Because we know gravity, and we know that it reaches the speed of 0. There's really 3 variables that we have to know to use these equations, and you know we can realize that it reaches a temporary final speed of v right at the point we're interested in, the top of its flight. So that's convenient. So you can do this, you know, when first you'll know the time because it's half the time airborne, right? Like. If the total time airborne is twice the time to max height, then half the time airborne, right, is lowercase t. So that times 9.8, that's how fast you do it, meters per second. Multiply it by 2.23, you got miles per hour. Yes, I think.
Wouldn't the fourth step be the same as squaring the initial and the final velocity?
This one?
Yes. So like if we did v squared equals v squared plus 2as, isn't that the same thing?
If you use this equation to solve it, then you would say, well, if you solve for the height first, then yeah. So, I mean, there's no time in that. So if you're using time, you could use time to calculate your height, and then that would be like your displacement. So that's like this. And then you're saying it reaches a speed of 0. So it's like how fast does something go that reaches the speed of 0 when it's twice the 9.8 for, you know, that height. And so this is just a way to sort of relate initial final velocity with acceleration with displacement. The displacement is like the height vector here. There's more than one way to do this for sure, but sometimes that introduces confusion. So let's forget about that unless you know you're comfortable with it and you're like, well, I'll just solve it this way. There's plenty of ways to go about it for sure. All right, so we want to say here is that we have to throw a ball, measure the time airborne t. Right, so we have, you know, that's step 1. Step 2, We're going to take that time t, divide it by 2 to get this time t. And then step 3, we're going to calculate height h as 1/2 gt squared. It's like one step leads to the next, right? Like we have to know this t before we can calculate the height. Calculate initial velocity. It's just going to be 9.8 times t. Okay? So these will give you answers, which then remember for this one, we're going to times it by 3.28 to get feet, because this will be meters, and this is how many feet per meter. This answer here will give you the velocity in meters per second, but if you multiply it by 2.23, you will get miles per hour. And this will be our midterm. Okay, so rather than taking a boring, like, multiple choice, true or false test, we're going to go out and launch some rockets and throw some tennis balls. Okay. The same physics for launching a rocket, like, okay, I'm going to throw a ball in the air, but then I'm going to, like, put a bunch of air pressure and water pressure inside of a 2-liter bottle, and I'm going to let that thing get launched up. So let it sort of deliver some force there, and we'll see who can win. Okay, so I'll launch a tennis ball with a rocket. You all get your arms, and we'll see who can go the highest and the fastest. Okay. So energy is neither created nor destroyed. And I pump this water rocket thing up, and you see like how many times I have to pump that, and you're like, well, that's a lot of like arm pushes. You know, like you get one arm push, but I'm going to really pump that thing up. Okay, and then you can kind of say, well, if energy is neither created nor destroyed, you put a lot of energy inside of that thing. That's not a fair fight. And that's sort of the point. Like, I don't think anybody's going to be able to achieve greater velocity or height than the rocket launch. Okay, but maybe. I've had some students have some impressive throws over the years. If you catch the tennis ball, I'm hesitant to say this, I always offer an automatic A for the year if you can catch the tennis ball. But it's just a joke anyway. Sometimes students are so like, trying to get tennis, like, we'll give you an A for the year. It's just a joke. But it's a good, claim to fame there. It's a good thing to be able to say that you've done. I got a tennis ball. Few students out. But one year, okay, it was a sad day out on the practice field. We had a student that was going for the tennis ball catch, but it was a lot of weight, okay, on the launch pad there. So it was hardly a big launch at all. It didn't go up that high. And I was standing over here, and the student that was launching was like pulling the ripcord, but the tennis ball was kind of coming my way. So I'm like, oh, I'm gonna catch it over here. But then the student was also like, I'm gonna catch it, wasn't aware of like I was right there and completely ran right into me. And like, knocked himself out. I was like, oh, you shouldn't play that game anymore. He wasn't knocked out. I mean, he was knocked down. He didn't like lose consciousness or anything. He was fine, broke his glasses, but he doesn't care. Because I'm like an immovable object, you guys. So he runs into me, it's just like, oh, there you are on the ground, and I'm just standing there unaffected by it. Okay. So let's launch some stuff here in the lab. Okay, that's what we need to do. Let's slide it all the way over here. This chalkboard now, and let's go ahead and see what the physics looks like for sort of launching downrange. So let's choose. I'll tell you that the velocity of this marble being launched right now is 8.28 meters per second. 8.28 meters per second. That's how fast that thing is left. I happen to just launch that at an angle of 37 degrees thereabouts. Let's change it to 40. So this is what I mean about sort of launching downrange. only this part of the velocity is affected by gravity, the vertical component. When you launch something up and to the right, you know, to my right, or to your left, up and at some other direction in the vertical horizontal directions, we resolve the vector, we find how much of that velocity is in the x direction, how much of that velocity is in the y direction. Because gravity only affects things in this direction, so we have to sort of break the velocity down into components. So with a little bit of trigonometry, you can do that. If you have ever heard of this mnemonic phrase, SOHCAHTOA, it's a way to remember that the sine of some angle is equal to the side opposite divided by the hypotenuse, opposite of the hypotenuse. The cosine of the angle is equal to the side adjacent, so next to that angle, divided by the hypotenuse, which is always the side opposite the right angle. And then the tangent relates the side opposite and the adjacent. So it's the ratio of this to this. Because this is opposite, this angle, and I know the hypotenuse is 8.28, and I can measure directly, okay, what that velocity is, then this is going to be related with the sine function. So we sort of like take this piece and say the sine of my angle 40 degrees is equal to a ratio opposite of the hypotenuse. So the side opposite is my y component of velocity, and the hypotenuse is 8.28 meters per second. Multiply both sides by 8.28 meters per second, and I can see that the y component is going to be the sine of 40 degrees times 8.28. And then the units here again are meters per second. So in my calculator, sine of 40, 0.64 times 8.28 gives me 5.3 meters per second, which if you're curious, it's about 11 miles per hour, about 12 miles per hour. This 8.28 meters per second, we just witnessed it fly across the lab there, times 2.23, that's about 20 miles per hour, left about 18 miles per hour, 18 and a half miles per hour. Down here, we want to calculate the range. Okay, like how far down range will this thing go? The range is equal to how fast it goes in the x direction times the total time airborne. Okay, so how fast does it move sideways times how long is it airborne? If we let it be airborne longer and it's moving this way, it's going to get further downrange. If it's moving faster this way, it's going to get further downrange. This is the side adjacent, so this little piece of it here, the cosine of that angle is equal to the side adjacent, which is the x component of velocity, divided by the hypotenuse again, meters per second. And so we can see how we calculate the x component as the cosine of the angle times 8.28 meters per second. So I've got the cosine of 40 degrees times 8.28, which yields a value of 6.34 meters per second. And so you can see how does 5.3 plus 6.34 add up to 8.28? So it doesn't, right? And this plus this is not this. But this squared plus this squared is indeed this squared, because it's a right triangle, and it's Pythagoras' theorem that relates it. So if you were to take 6.34 squared plus 5.3 squared, it's going to equal whatever 8.28 squared is. It'll be very close. I'm not going to go around, but that's Pythagoras' theorem, right? And that's another way that we could have solved like this one. We have to use the trick. Once we know two sides of it, we can say, oh, we'll just use Pythagoras' theorem to solve it. So the time is dependent upon how fast up we launch it. If I direct more of the object's velocity towards the vertical direction, I'm not going to launch this one as fast because it would hit the slow. Let me show you. I'll hit the ceiling if I launch as fast as I can. And that's like an outside force acting upon it. So we would just want to have gravity be the only force. So like an object in motion remains in motion, let's have gravity be the only outside force. So I'm going to launch at the same angle, but at a slower speed. This is 70 degrees. There's the launcher right there. You learners, 70 degrees. And we saw it landed a certain distance away. It goes up in the air and then falls down. So it had, if it's 70 degrees, more of the velocity is directed vertically, right? Anything greater than 45, this number would be bigger than this number. Anything less than 45, more of the velocity is directed this way. At 45 degrees, they're exactly the same. Okay? Because the cosine and the sine of 45 is the same value, so it's 0.707, something like that. Okay. So if we launch at a complementary angle, like not 70 degrees, what's the complement of 70 degrees? 20 degrees, right? Complementary angles out up to 90. So here's the same speed that I just launched it a moment ago. Outside forces acting upon it, you probably kick it with your gun. You might have noticed that landed in basically the same spot. Okay, this one was able to land there because it was moving much faster sideways, right? But it wasn't airborne as long because more of the velocity was directed this way. The first one was able to make it that far because while it wasn't going as fast sideways, it was airborne a lot longer. So this one has a higher max height, but it's not traveling as fast sideways. So it's like these are the two things that determine range. You go far down range because you're either airborne for a long time or you're moving really fast sideways. The time airborne is dependent upon how fast up you throw it or how high up you are. A pitcher, right, throws a ball, they're basically putting all of their velocity in the horizontal direction. So it goes down because of their height and the height of the pitcher's mount. Okay, like this launcher is above the table a little bit. Okay, so it's actually falling more than it's landing. We're sort of assuming that it's landing in the same place it's being launched, and that's not really true. The marble launcher is 26 centimeters above the ladder. So if we want to land at equal elevation, we're going to land it on our 26 centimeter tall box here, our 0.26 meter tall box. We're going to try the bullseye. All right. So let's go and calculate now. What is the range for this situation? First, we calculate the time airborne. We consider this same point up here that the velocity at that point goes to 0. And so the velocity equals the velocity final equals the initial velocity plus the acceleration times time. So 0 equals 5.3 minus 978 t. We subtract 5.3 from both sides. That is equal to negative 9.8 t. And then divide both sides by negative 9.8. So the time to max height is the velocity divided by the acceleration due to gravity. And for these initial conditions, we would calculate that time to max height to be 5.3 over 9.8 or 0.54 seconds. So we'll reach max height after just more than half a second, which means it should hit the ground after just over a second, 1.08 seconds, right? So we'll hit the ground. So that's this. We already figured out the x, and so now we've got 6.34 meters per second. Let something going that fast travel for 1.08 seconds. And how many meters away will it be? 6.8. 6.85. So 685 centimeters, or 6.85 meters. So that was at the conditions of a 40-degree launch. 8.28 meters per second. We go 1, 2, take a look at we're going 1, 2, 3, 4, 5, 6.85, right at the edge of the lab. So 685 centimeters away is right here. Got our bullseye target there. let's really quickly give ourselves a hypothesis about the maximum height here. So the maximum height, just like we said from before, is going to be 1/2 g t squared, and we know that t is going to be 0.54. So it's like if I drop something that fell for 0.54 seconds, how high up was it? Well, it's just going to be half of 9.8 times 0.54 squared. So that's what I mean. All you have to do is know the time and max height, and that equation, you got the height there. So 0.54 squared times 9.8 times a half, 1.42 meters, 142 centimeters, which is this ball right here. So it should go this ball at half the range, right? Like we doubled this time to get the total time airborne. So the half range would be half of this. So what's half of 6.85? 3.425. So after 123.425, it should be a maximum height, which is here. Let's test our prediction now. Downrange, you can see the top of that ruler. You can see the receptacle, our launch pad, or landing pad, I should say. I'd be really lucky if we were able to actually hit the top of that. Sweet. 3, 2, 1. So while the prediction of the height seemed pretty good, right? Like that was pretty good going there. It fell short. Fell short, huh? So that shows you how something like in chemistry, right? Sometimes we did a theoretical yield, we did an actual yield, it wasn't 100%. Sometimes the apparatus is a little bit uncertain, but it's still fun. We'll try it again. All right, so now we'd say, okay, we're not considering wind resistance. That's the problem. It's just gravity. There's wind. It's scratching all this air here in the lab, and we've seen both times it's fallen short. So I think that's going to be good for us now. Head my best. So keep in mind what went into the calculation. Did we account for everything? And I would say more so than the wind is like the uncertainty in the apparatus. Like every time, like this is always delivering the exact same force in the exact same way. 3, 2, 1. Even worse. I have a different marble, but I'm hesitant to launch it. So I got my triple beam balance here so we can see like, well, what about the mass of it? Does that affect it? But this is like a steel sphere rather than a plastic marble. You can kind of see the difference here. And go as far. And that's because it didn't leave with this velocity. Okay. I still have a photo gate timer on the apparatus, as you can see. It left at 0.0038 seconds, but this velocity is based on leaving in 0.0023 seconds. And so because this is, let's bring it all back together here now. Because the steel sphere has greater mass, right? The force that mechanism can deliver doesn't accelerate more massive things as much, right? So like Newton's second law tells us how much things accelerate according to the force in relationship to how massive it is. Like more massive things don't accelerate as much with the same force as less massive things. And so if I have a more massive steel sphere and a less massive plastic sphere, and the mechanism is delivering the same force, right? Like it's the same amount of energy stored in the spring, it's the same, force delivered each time. So why was there different accelerations? Because of the difference in mass. So matter, what you talked about yesterday, one of the definitions of mass is inertial mass, the tendency to resist change in motion. Because this is heavier, it tends to resist change in motion more. And yet, if I were to drop them, they should indeed hit the ground at the same time. All right, and so let's go ahead and get ready for the weekend here. can see that indeed that's the case. Keep the procedure in mind as we will go out to the practice field on the midterm. We'll see maybe some more of this next week. We'll continue on with the exact studies. All right, you learners, if you're good to go, have a good weekend. Everybody else, you can wait to the bell. The quiz should be, yeah, with your journal.